Here we have a depiction of a wave form. Let's say this is the fundamental waveform for a wave in a string. And another waveform here. This waveform perhaps representing the doubling of this frequency. We see 1, 2 complete cycles as this waveform makes 1 complete cycle. And of course then the cycles continue. Now, this is going to be somewhat similar to what you saw on the screen, the oscilloscope screen, when we played the different sounds, made the different sounds with the different instruments. If we add these two waveforms, well, how do we do that? We add the displacement from the equilibrium position of this waveform to the displacement of this waveform. Now I haven't drawn in the equilibrium position of the top wave, so let's attempt to do that. You see, for example, that when this waveform peaks, this waveform is fairly high, so that we're going to add these two and get a pretty high peak. Whereas when this one peaks, this one's back to 0. So it might not be as high here when we add the two as it is here. Because, as I said, this one's already pretty high and this one's at its peak. We just add all the way along. You see that there's a point here where this one's as high as this one is low. And there, the wave's going to cancel out pretty much. Now, to construct the sum of these two, what I do is I make a dotted line, a dotted curve, that follows the pattern of the fundamental curve. This might be your fundamental mode. This might be your octave. Okay, twice the fundamental mode, the first overtone, in other words. If I add this shape to the dotted line shape by adding the height of this graph at every point, I might end up with something that looks like this. Now, the exact form of this curve depends on the amplitude of this wave and the amplitude of this wave. But what we get might plausibly look something like this. Actually, I think what I've added here is probably the second wave might have a little less amplitude than what I've drawn here. Okay, because this one doesn't come up quite as high above the dotted line curve as this one does above equilibrium, and it should. So this thing really should be a little more extreme up here and then so forth. In any case, this is how we add the two frequencies, and we get these strangely shaped waves like the ones that we've seen on the oscilloscope. Now the intensity graphs, okay, the strength of the different harmonics might have looked something like this, where we have the frequency here and we have the intensity here. Now for the graph I just did, we had a fundamental frequency in the first overtone, which is double the fundamental frequency. We had a little bit more of the fundamental than we had of the doubling. So the intensity of the fundamental was somewhat higher than the intensity of the first overtone. This would be a graph of intensity versus frequency for the components of that wave. For a typical voice or instrument, or maybe the chimes, the intensity versus frequency graph might look like this, where we have the fundamental frequency and some overtones in the vicinity of the fundamental, double the fundamental, some overtones in the vicinity of that frequency, triple the fundamental, some overtones in the vicinity of that frequency. Okay? So we have the fundamental, the first overtone, the second, or, if we wish, the first, second, and third harmonics, with the first being stronger, and the second a little less strong, and the third even less strong than that. The mix of these frequencies is what determines the tone of a sound.